The James Webb Space Telescope has just confirmed a discovery so profound that it is rewriting the very timeline of cosmic history. A single galaxy, blazing with impossible brilliance when the universe was barely 280 million years old, has emerged from the deepest reaches of space and time. This is not merely the most distant object ever detected. It is a luminous anomaly whose very existence challenges the foundational story of how matter, stars, and structure came to be. Astronomers are now grappling with a reality that feels almost unreal. The infant universe was not a dim, hesitant void slowly awakening. It was already ablaze with activity, forging complexity at a pace no model ever predicted. To grasp why this moment is so seismic, we must step back to the era before this telescope unfolded its golden gaze. The previous champion of distance was a faint, reddish speck known as GN-Z11, captured by the Hubble Space Telescope. That fragile glow represented a monumental achievement. Hubble had already revolutionized cosmology, unveiling galaxies stretching back billions of years and proving the cosmos was vaster and more intricate than any prior generation dared imagine. Yet even its legendary vision had a frontier it could not cross. A veil of red-shifted light where the earliest galaxies hid, their ultraviolet emissions stretched into invisible infrared by the universe's relentless expansion. The Webb telescope was engineered precisely to shatter that barrier. With a mirror spanning nearly 7 meters and instruments exquisitely sensitive to infrared wavelengths, it was built to capture the faintest whispers from the cosmic dawn. From its very first deep fields, it began exceeding every expectation. Galaxies appeared where theory suggested only sparse, embryonic clouds should exist. Records fell in rapid succession as objects with redshifts beyond 13, then 14, materialized in the data. Each new detection pushed the observable boundary closer to the Big Bang itself, revealing a universe that seemed eager to reveal its earliest secrets. And then came the breakthrough that astronomers now call a cosmic miracle. In a patch of sky meticulously surveyed over hundreds of hours, Webb locked onto an object designated MOM-Z14. Its light has journeyed across 13.6 billion years to reach us, originating when the universe was less than 300 million years old, a mere infant in cosmic terms. What stunned researchers was not just its distance, but its radiance. This galaxy shines with a luminosity far exceeding anything permitted by standard models. It is forming stars at a rate that would require an extraordinary concentration of gas and an efficiency of conversion that defies conventional physics. In an era when the first stars should still have been struggling to ignite, this object glows as if the entire process of cosmic maturation had been dramatically accelerated. Even more startling is its apparent structure. Though compact, spanning perhaps only a few thousand light-years, it harbors a stellar population that appears surprisingly developed. Spectral analysis reveals emission lines indicating vigorous ionization and the presence of heavier elements scattered through its gas. These chemical signatures imply that generations of massive stars had already lived explosive lives, enriching the surroundings with metals forged in their cores. In the standard timeline, such enrichment should take far longer. The raw universe emerging from the Big Bang consisted almost entirely of hydrogen and helium, with trace lithium. Building significant quantities of carbon, oxygen and beyond demands cycles of birth, fusion, and supernova death. For MOM-Z14 to display this level of chemical maturity suggests that star formation ignited earlier, burned hotter, and spread its products faster than any simulation ever forecasted. This single galaxy is not an isolated outlier. Webb's deep surveys keep uncovering similar beacons, compact, intensely luminous sources that populate the early universe in numbers far greater than predicted. These objects, sometimes described as unusually radiant for their epoch, appear repeatedly in the data. Their abundance creates a profound tension with cosmology's core framework. Our models, built on decades of observation and theory, anticipate a gradual build-up. Sparse halos of dark matter slowly gathering pristine gas, cooling haltingly, forming modest first stars known as population 3. Those stars should illuminate the cosmos dimly at first, ionizing the neutral hydrogen fog only after billions of years of collective effort. Yet the reality Webb reveals is one of precocious brilliance, where substantial galaxies already thrive in an era once thought barren. The implications ripple outward. If galaxies like MOM-Z14 are commonplace, then the process of structure formation must have been far more efficient in the early universe. Gravity alone, acting on cold dark matter, may not suffice to explain such rapid assembly. Feedback from the first stars, supernovae, winds, radiation, should have impeded rather than accelerated growth. Instead, we see evidence of the opposite. Conditions that somehow funneled gas inward with extraordinary speed, igniting furious bursts of starbirth. This does not overturn modern cosmology outright, but it exposes deep incompleteness. The cosmic dawn was not a gentle twilight. It was a violent, incandescent eruption that sculpted complexity almost immediately after the Big Bang's afterglow faded. And this is merely the opening chapter. Upcoming surveys with Webb and future observatories will probe even wider swaths of sky with greater depth. Hundreds, perhaps thousands, of such luminous early galaxies await discovery. Each one will refine, or further strain, our understanding of those primordial epochs. Yet even as these observations reshape the narrative of galaxy birth, a more daring hypothesis has begun to gain traction among theorists, seeking to explain the impossible brightness of objects like MOM-Z14. What if some of these radiant sources are not ordinary galaxies at all, but something far more exotic? Dark stars? This concept, once confined to the edges of theoretical speculation, has surged in prominence as Webb's data accumulate. Dark stars arise in models where dark matter particles possess the ability to annihilate upon collision, converting mass into energy. In the dense cores of the earliest protostellar clouds, such particles could concentrate, generating immense heat through ongoing annihilation. This heat would sustain the object against gravitational collapse, allowing it to swell to extraordinary size, hundreds of thousands, even millions of times the Sun's mass, while radiating prodigiously without relying primarily on nuclear fusion. From our perspective, a dark star would appear as an intensely bright, reddish point of light, its spectrum shaped by the vast envelope of hydrogen enveloping the annihilation-powered core. As the surrounding dark matter density thins over time, the heating diminishes and the object transitions to ordinary fusion, briefly blazing even brighter before collapsing into a massive black hole. This final implosion would seed the supermassive behemoths observed at the hearts of early quasars, explaining how billion solar mass black holes could exist when the universe was less than 1 billion years old. The match between predicted dark star signatures and certain Webb detections is striking. The extreme luminosity, the compact appearance, the absence of certain expected heavy element features that normal stellar populations would produce. If dark stars truly dominated the cosmic dawn, the consequences would be staggering. They would illuminate and ionize the universe far more effectively than standard population 3 stars, clearing the intergalactic fog sooner and enabling the rapid galaxy buildup we now observe. More profoundly, their existence would constitute direct evidence of dark matter's microscopic properties, its particle mass, its self-interaction strength, perhaps even its role in the asymmetry between matter and antimatter. The early universe would become a laboratory for particle physics on grandest scale, where the invisible substance shaping cosmic structure also powered its first lights. This perspective also addresses deeper mysteries. The extraordinary efficiency needed to form luminous galaxies like MOM-C14 could stem not from unknown astrophysical tricks, but from the hidden energy source within dark stars themselves. Their prolonged, stable phase would allow vast amounts of pristine gas to accrete before fusion ignites, producing the observed bursts of star formation upon transition. Patterns in the distribution of these early bright sources might even encode information about dark matter's primordial fluctuations, offering clues to physics operating at energies far beyond earthly accelerators. Of course, alternative explanations remain viable. Some researchers argue that dust obscuration, extreme stellar feedback, or underestimated star formation efficiency in dense primordial gas could account for the brightness without invoking new entities. Improved modeling of gas dynamics and radiation transport might reconcile the observations with conventional cold, dark matter. Statistical effects in small survey volumes could exaggerate the apparent overabundance. Yet with each new Webb dataset, the tension grows, and the dark star hypothesis gathers momentum as an elegant solution to multiple puzzles at once. Whatever the ultimate resolution, one truth stands undeniable. The universe persists in defying our neatest theories. From impossibly radiant galaxies shining in cosmic infancy, to the tantalizing possibility of stars fueled by the invisible substance holding everything together, the cosmos reveals layer upon layer of unexpected depth. MOM-14 and its kin are not mere data points. They are emissaries from an era we are only beginning to comprehend, carrying messages that demand we expand our vision. As Webb continues its relentless gaze into the abyss, it becomes ever clearer that the universe guards its deepest truths jealously. This unfolding epic is not simply about distant lights or esoteric particles. It is about the nature of existence itself, a vast, dynamic tapestry far stranger, more efficient and more wondrous than any story we once told. And in contemplating these revelations, we confront the most exhilarating mystery of all. In a cosmos capable of such rapid, hidden brilliance, what role do we, brief sparks of awareness, truly play? What do you believe these ancient beacons are trying to tell us about the universe's hidden heart? Share your thoughts below. And if this journey into the cosmic dawn has ignited your sense of wonder, join us for the discoveries yet to come. Subscribe, turn on notifications, and share this exploration with others who yearn to see the universe unveiled. The next revelation is already on its way.